Dynamic AMOLED. Dynamic AMOLED is another evolution of Samsung's OLED technology, designed not only to improve picture quality but also to make displays more comfortable and safer for long periods of use. Rather than introducing a completely different type of screen, Dynamic AMOLED combines several hardware and software improvements into a single premium display. One of its biggest upgrades is support for High Dynamic Range, or HDR. Specifically, many Dynamic AMOLED displays are certified for HDR10+, allowing them to reproduce a much wider range of brightness and color than standard displays. This makes movies and videos appear closer to what filmmakers intended, with brighter highlights, deeper shadows, and smoother transitions between light and dark areas. Brightness itself also improved significantly. Dynamic AMOLED panels can reach extremely high peak brightness levels when needed, making them much easier to read under direct sunlight. At the same time, they can lower their brightness to very comfortable levels for reading in dark environments without causing unnecessary eye strain. Samsung also focused on color accuracy. Earlier AMOLED displays often emphasized vivid colors, but Dynamic AMOLED panels are generally calibrated to produce more realistic tones while still offering the option of a more vibrant display mode. This allows users to choose between professional-looking color reproduction and a more colorful viewing experience. Another major improvement involves blue light. Scientific research suggests that excessive exposure to blue light, particularly late at night, may interfere with natural sleep cycles for some people. Dynamic AMOLED displays are designed to reduce harmful blue light emissions without relying entirely on software color filters that make the screen appear heavily yellow. As a result, the image retains much of its natural appearance while potentially reducing eye fatigue during extended use. Motion handling also became smoother. Many Dynamic AMOLED displays support adaptive refresh rates, allowing the screen to change its refresh rate automatically depending on what is being displayed. Reading a static article may require only a low refresh rate, while fast-paced gaming or scrolling instantly switches to a much higher one. This helps balance smooth performance with battery efficiency. Contrast remains one of Dynamic AMOLED's greatest strengths. Because every pixel emits its own light, black areas remain perfectly dark while bright objects stand out dramatically against them. This creates a level of visual depth that continues to distinguish OLED technology from traditional LCD displays. The display is also capable of reproducing a very wide color gamut, allowing it to display subtle shades that older smartphone screens could not accurately reproduce. Professional photographers, video editors, and designers benefit from this improved precision when reviewing their work directly on a mobile device. Dynamic AMOLED panels are typically protected by advanced cover glass and paired with ultrasonic or optical fingerprint sensors hidden beneath the display. This creates a cleaner front design while maintaining secure biometric authentication without requiring a separate physical fingerprint reader. Although Dynamic AMOLED remains primarily associated with Samsung's flagship devices, many of the technologies introduced alongside it have influenced the broader smartphone industry. Features such as adaptive refresh rates, improved HDR performance, reduced blue light, and higher brightness have gradually become expectations for premium smartphone displays regardless of manufacturer. Today, Dynamic AMOLED represents one of the most refined forms of OLED technology available in consumer smartphones, combining exceptional image quality with features designed to improve both comfort and everyday usability. LTPO OLED. Low-temperature polycrystalline oxide OLED, commonly called LTPO OLED, is one of the most important advancements in modern smartphone displays. While the picture quality looks very similar to other high-end OLED panels, the real innovation is hidden beneath the pixels. LTPO changes the way the display controls its refresh rate, allowing it to become far more energy efficient without sacrificing smooth performance. To understand why LTPO matters, it helps to know what a refresh rate is. Every display redraws its image many times each second. A standard screen may refresh 60 times every second, while newer smartphones often refresh at 120 times per second. Higher refresh rates make animations, scrolling, and gaming appear much smoother, but they also require more power because the display is constantly updating the image. Earlier OLED displays could switch between a few fixed refresh rates, such as 60 Hz and 120 Hz. Although this helped save some battery life, it was not always efficient because many tasks did not need such frequent updates. Reading an ebook or viewing a still photograph requires almost no motion, yet the display might continue refreshing dozens of times every second. LTPO solves this problem by allowing the refresh rate to change across a much wider range. Depending on what is happening on the screen, the display can refresh at 120 Hz during fast gameplay, drop to 30 Hz while watching certain videos, or even fall as low as 1 Hz when showing an always-on clock. The transition happens automatically and usually goes unnoticed by the user. This adaptive behavior greatly improves battery life. Since refreshing the screen consumes energy, reducing unnecessary updates means less power is wasted. Over the course of a day, these small savings can add up, especially for people who spend many hours using their smartphones. Another benefit is that users no longer need to choose between smooth performance and long battery life. Before LTPO became common, enabling high refresh rates often meant noticeably shorter battery endurance. With LTPO, smartphones can provide fluid animations when needed while conserving energy whenever possible. Apple was among the companies that helped bring LTPO technology to mainstream smartphones, introducing it in selected premium models under the marketing name promotion. Samsung and several Android manufacturers also adopted LTPO panels in their flagship devices, making adaptive refresh rates a defining feature of high-end phones. LTPO also improves the experience of always-on displays. Since the screen can refresh as slowly as once per second, the phone can keep showing the time, notifications, or small widgets while consuming surprisingly little power. This makes always-on features practical for everyday use without significantly affecting battery life. The technology becomes even more valuable as smartphone processors and graphics hardware continue to grow more powerful. Games and applications increasingly support refresh rates beyond 60 Hz, and LTPO allows the display to deliver this smooth experience only when it is truly beneficial. Although LTPO panels cost more to manufacture than conventional OLED displays, many experts consider the additional efficiency worth the expense. It represents a major step toward smarter displays that adapt their behavior to the user's activity rather than operating at a fixed speed all the time. Today, LTPO OLED has become one of the defining features of premium smartphones. While users often notice the smooth scrolling and responsive animations, the greatest achievement happens quietly in the background, reducing power consumption every second the display is in use. P-OLED. Plastic OLED, usually shortened to P-OLED, is an OLED display built on a flexible plastic substrate instead of traditional glass. Although the pixels produce light in the same way as other OLED screens, replacing the rigid glass layer with plastic changes how the display can be manufactured, shaped, and used. The word plastic can be misleading. It does not mean the display feels cheap or fragile. In fact, the plastic substrate sits beneath several protective layers, including strengthened glass or other durable materials that users actually touch. The plastic is hidden inside the display and serves as a flexible foundation for the light-emitting layers. One of the biggest advantages of P-OLED is flexibility. Since the display is no longer built on rigid glass, manufacturers can gently bend the panel during production. This allows companies to create curved smartphone screens, wrap displays around the edges of devices, and design products with more creative shapes than traditional flat displays allow. P-OLED is also lighter than many glass-based OLED panels. Reducing the weight of the display contributes to lighter smartphones, which can improve comfort during long periods of use. Every gram matters when manufacturers are trying to balance large batteries, powerful cameras, and premium materials. Durability can also improve in certain situations. Glass is naturally brittle and may crack when subjected to heavy impacts. A plastic substrate is more flexible and can absorb some stress before breaking. Although the protective cover glass on top can still shatter if dropped, the display beneath may survive impacts that would otherwise damage a rigid panel. Another advantage is manufacturing freedom. P-OLED panels can be produced with extremely thin bezels because the display circuitry can be folded behind the visible screen area. This technique, often called display folding or panel bending, allows manufacturers to maximize screen size without making the phone physically larger. Companies such as LG Display became well known for producing P-OLED panels, supplying them for smartphones, automotive displays, and wearable devices. The technology also plays an important role in foldable smartphones, where the ability to bend repeatedly is essential for the device to function properly. Image quality remains very similar to conventional OLED because both technologies rely on self-emitting organic pixels. Users still enjoy deep blacks, excellent contrast, vivid colors, and fast response times. Most differences lie in the physical construction of the display rather than the image itself. However, manufacturing P-OLED panels is more challenging than building traditional rigid displays. Engineers must ensure that flexible materials remain reliable after repeated bending, changes in temperature, and years of daily use. Developing durable hinge mechanisms for foldable phones has required significant engineering advances alongside improvements in the displays themselves. As foldable devices become more common, P-OLED has become increasingly important. It demonstrates how changing the foundation beneath the display can unlock entirely new product designs while preserving the visual advantages that made OLED technology so popular. Foldable OLED. Foldable OLED is a specialized evolution of OLED technology designed to bend repeatedly without losing image quality or structural integrity. Unlike traditional rigid displays, it is built on flexible materials that allow the screen to fold inward or outward, making modern foldable smartphones possible. At the core of foldable OLED is the same principle as standard OLED: each pixel emits its own light. The major difference lies in how the layers above and below those pixels are engineered. Instead of using rigid glass as the base, manufacturers rely on ultra-thin flexible substrates that can withstand constant bending stress. To make this possible, every layer of the display must be redesigned. The organic light-emitting materials, thin-film transistors, and protective encapsulation layers are all optimized to remain stable even when the screen is folded thousands or even hundreds of thousands of times. This required years of material science development to ensure long-term durability. One of the most visible benefits of foldable OLED is the ability to transform a phone's form factor. A device can behave like a regular smartphone when closed, then unfold into a much larger screen resembling a small tablet. This dual experience changes how users interact with content, especially for multitasking, reading, and media consumption. Despite being flexible, foldable OLED displays still maintain the core visual strengths of OLED technology. Deep blacks, high contrast, vibrant colors, and fast response times remain intact. In fact, because these displays are often used in premium devices, manufacturers tend to calibrate them for very high brightness and color accuracy. The folding mechanism itself introduces unique engineering challenges. The display must bend at a very tight radius, especially in inward folding designs. To reduce stress at the fold point, manufacturers often use special layered structures, including ultra-thin glass combined with polymer layers, to distribute pressure more evenly across the screen. A visible crease in the middle of the screen is a common characteristic of foldable displays. This happens because the same area is repeatedly bent. While modern engineering has reduced the visibility of the crease significantly, it is still a natural result of the physical stress placed on the material. Durability has improved dramatically over generations. Early foldable OLED devices were fragile and sensitive to dust or pressure. Newer models include stronger protective layers, improved hinges, and better sealing systems that help prevent particles from entering the folding mechanism. Foldable OLED also changes how software behaves. Applications are designed to adapt dynamically when the screen changes size. A phone can switch from a compact interface to a multi-column layout instantly, allowing users to run multiple apps side by side in a way that was not practical on traditional smartphones. Battery consumption is carefully managed in foldable devices. Since the displays are larger when unfolded, power demand increases. However, OLED efficiency helps offset this, especially when parts of the screen display dark content or remain unused during split-screen multitasking. Companies like Samsung have been the main drivers of foldable OLED development, releasing multiple generations of foldable smartphones that gradually improved in durability and usability. Other manufacturers have also entered the space, experimenting with different folding styles such as book-style folds and clamshell designs. Foldable OLED represents not just an improvement in display technology, but a shift in how smartphones are physically designed. It opens the door to devices that can adapt their shape to the user's needs, rather than forcing users to adapt to a fixed screen size. Mini-LED. Mini-LED is an advanced backlighting technology used in LCD displays to significantly improve contrast, brightness, and local dimming performance. While it is not a self-emissive technology like OLED, it enhances traditional LCD panels by using thousands of much smaller LEDs as the light source behind the screen. In a conventional LCD, a relatively small number of large LEDs provide uniform backlighting across the entire display. This limits contrast because the screen cannot precisely control which areas should be bright or dark. Mini-LED changes this by dramatically increasing the number of individual backlight zones. Each mini-LED zone can be controlled independently, allowing the display to dim or brighten specific regions of the screen. When a scene contains both bright highlights and dark shadows, the backlight can adjust in those areas separately, producing much deeper blacks and more realistic contrast than standard LCDs. This improvement makes mini-LED displays much closer in visual quality to OLED, especially in terms of contrast. However, since the light still comes from a backlight layer rather than individual pixels, true pixel-level black is still not possible. Some light leakage, known as blooming, can sometimes appear around bright objects on dark backgrounds. One of the biggest strengths of mini-LED is brightness. Because many small LEDs can work together, these displays can achieve extremely high peak brightness levels. This makes them ideal for HDR content, where bright highlights like sunlight reflections or explosions need to stand out clearly. Mini LED also improves durability compared to OLED. Since it does not rely on organic materials, there is no risk of burn-in. This makes it especially useful for devices that display static content for long periods, such as monitors, professional editing displays, or productivity-focused tablets. Apple played a major role in popularizing Mini LED technology in consumer devices, using it in high-end tablets and laptops marketed as liquid Retina XDR displays. Other manufacturers have also adopted similar systems for premium monitors and televisions. Despite its advantages, Mini LED is still more complex and expensive to produce than standard LCD backlights. The large number of LEDs and precise local dimming zones require advanced manufacturing techniques and careful calibration to ensure consistent image quality. Mini LED is often seen as a bridge between traditional LCD and OLED. It does not fully replace OLED's pixel-level control, but it significantly narrows the gap in contrast and HDR performance while maintaining strong brightness and reliability. MicroLED. MicroLED is considered by many display engineers to be one of the most promising display technologies ever developed. It combines several of the best qualities of OLED and LCD while avoiding many of their weaknesses. Although MicroLED is still rare in smartphones because of its manufacturing complexity, it represents a possible direction for the future of mobile displays. Like OLED, every pixel in a MicroLED display produces its own light. There is no need for a separate backlight, so each pixel can switch on or off independently. This allows the display to create true black levels and extremely high contrast because black pixels simply remain off. The major difference between OLED and MicroLED lies in the material that produces the light. OLED relies on organic compounds that gradually wear out over time. MicroLED uses microscopic inorganic light-emitting diodes instead. These tiny LEDs are much more resistant to aging, allowing the display to maintain its brightness and color accuracy for much longer. Each MicroLED is incredibly small. Millions of these microscopic light sources must be placed onto the display with extraordinary precision. This manufacturing process is one of the greatest engineering challenges facing the technology today. Even a tiny alignment error can affect image quality, making production both slow and expensive. Brightness is one of MicroLED's greatest strengths. Because inorganic LEDs can generate much more light than organic materials, MicroLED displays can achieve extremely high brightness levels without sacrificing image quality. This makes them exceptionally easy to view outdoors, even under strong sunlight. Energy efficiency is another important advantage. Since each pixel produces only the light it needs, the display avoids wasting energy on unused areas of the screen. Combined with the high efficiency of inorganic LEDs, MicroLED has the potential to provide excellent battery life while maintaining outstanding image quality. Color accuracy is also impressive. MicroLED can produce a wide color gamut with excellent consistency, making it suitable for professional photography, video editing, and other applications where precise color reproduction is essential. Unlike OLED, MicroLED is highly resistant to burn-in. Because the inorganic LEDs degrade much more slowly, static interface elements are far less likely to leave permanent marks on the screen. This could make MicroLED particularly attractive for devices that display the same interface elements every day. Another advantage is lifespan. A MicroLED display can potentially remain bright and color accurate for many more years than current OLED technology. This longer operational life is especially valuable for premium devices that users intend to keep for extended periods. Despite these remarkable benefits, manufacturing remains the biggest obstacle. Building millions of microscopic LEDs and positioning each one perfectly requires highly advanced equipment and extremely precise production techniques. As a result, MicroLED displays are currently very expensive and are mostly found in specialized products or experimental devices. Researchers continue to improve manufacturing methods every year, and many experts believe costs will gradually decrease as production technology matures. If that happens, MicroLED could eventually become one of the most important display technologies in smartphones, combining OLED's perfect contrast with greater brightness, longer lifespan, and improved durability.